So we will start now with a presentation of one of the future ones, the hyperspectral mission, CHIME. And this will be presented by the mission scientist for CHIME, Marco Celesti. So just to say that for the operating missions, we have the presentation by the mission manager in charge of the operations. While for those are being developed, the presentation is by the mission scientist, who is in charge of more of the requirements and following up the development. So please, Marco.
Thank you for the introduction. Indeed, I'm the mission scientist for CHIME, but I'm presenting here on behalf of a much larger group, which comprises people from ESA and outside, say in the scientific community who's supporting the mission development. CHIME is part of the Copernicus expansion mission, which are six future Copernicus missions. The expansion mission are supposed to and meant to, let's say, to expand the current capability of the first six Copernicus missions. And CHIME in particular will look at, let's say, applications linked to soil, agriculture, crops, and raw materials as primary objectives, without forgetting a number of secondary objectives, let's say, and application areas, which will be covered by the very versatile nature of the measurements of CHIME. So what are these measurements? Let's start with a bit of principles of imaging spectroscopy. In short, for each pixel in the swath which is observed by the imaging sensor, you will have the full spectral signature of the surface. So what we mean by full spectral signature, basically, it's a continuous sampling with a distance between each band of around 10 nanometers in the spectral range between 400 and 2500 nanometers. And this will be done routinely over all land and coastal areas up to 370 kilometers offshore, with a resolution of 30 meters. A single acquisition has a swath of 130 kilometers, and basically every 11 days with 2 satellites flying, we have global coverage. So every 11 days we have another observation, a new measurement with the same observation geometry and the same, over the same, exactly the same surface with the same observation. We are developing some core data products which are, let's say, similar, at least conceptually, to those that you are familiar with, maybe with Sentinel-2 and Sentinel-3. So top of atmosphere radiance, the spectral radiance that we measure from the instrument for each of these bands. Then the reflectance, which is basically conversion using the extraterrestrial solar radiance and the cosine of the sun zenith angle, and then the bottom of atmosphere reflectance. So after the atmospheric correction, which for optical data is extremely important in order to get then to the real information, which is let's say on the properties of the surface we are observing. Okay, all these will be generated with uncertainties associated to each of these products in order to make a more sensible use of them into any workflow which will come after that. Because in the end, the real target of our mission, let's say, is not in these core products. These core products are meant then to be used for the many applications and both, let's say, more scientific and more operational that will come out of the CHIME measurements and core products. We are developing some of these, let's say, higher level products, which are targeted, of course, at the main applications which are driving our development, as I mentioned before. So agriculture and minerals exploitation, and so here I've just listed those which we are actively working on during the mission development. But we are also, let's say, working on the preparation of a number of additional products which will come up then in the exploitation phase when CHIME will be launched and will be flying. Then very briefly, a couple of examples of a bit more targeting, let's say, the main topic of this training school is not necessarily the most, say, emergency related mission that we have out there, but certainly it covers a large spectrum of the wavelength range, so it can be used for many things, and it feels very well holes that we have, for example, in other optical observations in spectral regions which are not covered, for example, by Sentinel-2. And some of these regions are very important, for example, for the cryosphere, and some have also implications for the hydrosphere, let's say, for hydrology studies, for example, when it comes to the snow melt. Okay, which is influenced by a number of factors. With optical imaging spectroscopy data, we can retrieve information on the snow grain size, and we can also map the 3 phases of water. So basically, the water vapor in the atmosphere, liquid water on the surface, and solid water, snow and ice. Very shortly, we are in phase C. The mission is in development, is in full steam, and the first CHIMES satellite will be ready for launch, basically starting from the third quarter of 2028. We have a number of cooperation with the other space agencies which are working on other hyperspectral mission in order to, let's say, create a constellation, a harmonized constellation of imaging spectroscopy missions in space. With this, I thank you, and I hope I was short enough.
Thanks a lot. Any questions for Marco about the CHIMES?
Thank you so much for the presentation. I'm wondering about mission CHIMES, if it will be compatible with previous operational mission like ENMAP and PRISMA.
Yes, this is a good question. In principle, when you look at the specification, in many ways we are close to ENMAP and PRISMA. In some case, we are doing better than those. And the idea behind CHIME is basically to bring to an operational level what today is observed by these sort of precursor missions, because ENMAP and PRISMA are doing great, but they observe on a tasking basis 30 by 30 kilometers basically of the surface of the Earth in a non-systematic way, meaning that they are tasking missions. So they are basically targeting spots on the ground based on the planning. CHIME will acquire routinely the whole globe, then limited a bit by the acquisition mask. So, but all land and coastal areas routinely. So with 2 satellites in orbit every 11 days, you will have an observation which is similar, if not better, to what you get today from ENMAP and PRISMA in a, let's say, non-systematic way. I hope this answers your question.
Is there another question? If not, we will move on to the next presentation. So thank you very much, Marco.
Thank you all, and have a nice training school.
Thank you. You too. And then we will start with the operational Sentinels. So first one out will be Sentinel-1, presented by the mission manager Nuno Miranda.
Good morning to all of you. My name is Nuno Miranda, and I'm the Sentinel-1 mission manager. So as requested by Espen, I will try to give you in a few minutes, in a few slides, a brief overview of what are the Sentinel missions. So before starting to that, diving into the Sentinels, I'd like to start this presentation by widening a bit the landscape with what are the ESA observation programs that is composed by 3 pillars. I think that the first pillar that you have here on the left-hand side is our science pillar that aims at consolidating science in the measurement of some particular bio-geophysical variables. And for that, we put in space very ambitious instruments like, you can see here the full family here, but you have 2 new satellites that we are building, like Biomass and Harmony, that are fantastic stars that will soon join the Earth Explorer family in space. The second pillar is the Copernicus program. This is the operational mission. Those are operational missions which target the development of operational applications, commercial services, and also support the implementation of European policy. So in flight here you have the family of the Sentinels, for which we have here Sentinel-1A, 1B, that are currently flying. That will be soon replaced by Sentinel-1C and 1D. And in this Copernicus program, you can see the Copernicus expansion missions like CHIMES that we have seen, but also Roselle, which is a tailband that will be presented later by Malcolm. We are also working towards Sentinel-1 next generation that will fly, or that will replace the current generation in the next decade. The third pillar that I want to discuss here is a Meteor component, for which ESA is developing the satellites that are operated by our sister agency, EUMETSAT. So the previous slide was basically talking about the future, and this slide just gives a brief recall about the past, because I used to say that Sentinel-1 is standing a bit on the shoulder of precursor missions like ERS and ASAR, and also the Canadian FLRSAT missions. And those missions, ERS, ASAR, that have been key and necessary to develop most, if not all, the applications that are now operational with Sentinel-1. And I think that's something that is extremely important for the users that are start using Sentinel-1 data, is to recall them that it's not only Sentinel-1, but they have the chance, real chance to have more than 30 years of data record at C-band. That is also complemented with other missions at mostly X-band and L-band. So let's go now more into Sentinel-1. The mission profile is basically a constellation of two satellites, two identical satellites that carrying a SAR at C-band. So today we are flying the A and B units. The B unit have been failed 2 years ago, and that will soon be replaced by the C unit, we hope next year. They are near polar, sun-synchronous, having a down-dusk orbit, and they are flying at an altitude around 700 kilometers. Each of them has a lifetime of 7 years, and they have a consumable for 12 years, meaning basically that they have fuel hydrazine for 12 years. And they have a 12 days repeat cycle, each one, and if you take into account the constellation, so the two satellites, they have a 6 days repeat cycle. The payload, as I've been mentioning, is a C-band SAR payload that has a center frequency very similar to what we have seen in the past with ASAR and ERS and also FLRSAT missions. It has several polarizations, so single pole and dual pole capacity. I think that Sentinel-1 has been the first mission acquiring data systematically in dual pole. Most of the Sentinel-1 data is now acquiring dual pole. Is that there's a very stringent radiometric accuracy of 1 dB 3 sigma. I think that this is super important for people willing to use this data in order to retrieve geophysical or biophysical variables, and a very stringent radiometric stability as well. One of the main characteristics is a noise equivalent sigma 0, which is extremely important for people that is willing to use the data at very low signal conditions. In addition to the C-band SAR, Sentinel-1 C and D, not A and B, C and D will carry another payload, which is an AES for marine surveillance. In terms of imaging modes, so we do have 4 exclusive imaging modes. Strip map mode, which is a legacy mode from ERS and NBSAT that is rarely used for Sentinel-1. We just use it over some small islands that that fits entirely in the 80 km swath of the strip map mode. This mode has the highest resolution. It has a resolution of 5 by 5 meters. The main mode of for Sentinel-1 is the interferometric wide swath, IWS, that has a very large swath of 250 kilometers and a resolution of 5 by 12 meters. This is the main mode that we use over the land masses. We also have another mode, which is the extra wide, that we use more over polar areas, that has a very large, an even larger swath of 400 kilometers at the expense of a poorer resolution with respect to IW, which is 20 by 40 meters. Over oceans, and we'll see that later, we are basically, I think the unique mission that are systematically acquiring in wave mode, which is a kind of reduced sampling, spatial sampling strip map that has a very high resolution of 5 by 5 meters with images acquiring leapfrog sample by 20 by 20 kilometers. I think that now the Gaufen satellite, Gaufen 3 is also having a wave mode. In terms of programmatics, we'll see that later. Sentinel-1C we hope will be launched in 2024, and Sentinel-1D that is currently in storage will be launched soon after. One of the main the main characteristics of the mission is that it acquired the data systematically over a predefined observation scenario. I think this is something that the user community have been mentioning quite a lot of time. They want to have a very stable and a fixed imaging scenario, observation scenario, such that they know that over a certain area the acquisition are guaranteed. And we have a very large duty cycle of 25 minutes per orbit. Now we are more outside the eclipse, we are around 30 minutes per orbit, that allow us to acquire data globally. One of the main also characteristics of Sentinel-1, like for all the Sentinels, is that it's full free and open. I'll skip this slide because it's just present the imaging modes that I've been discussing. The main mode of acquisition over land is this one, is IW mode. In terms of programmatics, again, so these slides basically represent the timeline of the Sentinel-1 first generation. The mission is running in a bit complex or difficult context in this moment because, well, let's try to recap from the beginning. So we start Sentinel-1, we launched Sentinel-1 back in 2014, sorry, and that has been followed by Sentinel-1B in 2016. The mission operated nominally up to the premature failure of S1B in December 2021, so that the entire Sentinel-1 mission is now fully relying on the Sentinel-1A spacecraft. So we are really looking forward to have a launch of a Sentinel-1C next year. The launch of Sentinel-C should have been in May this year. It has been postponed to December this year, and another time we hope to summer next year due to the problems that we have currently in Europe with our launchers. Sentinel-1D will be launched soon after Sentinel-1C in order to give rest to the unique flying unit that we have so far, which is Sentinel-1. That we will believe that once we have reestablished the constellation, we'll let Sentinel-1A in parking in orbit in order to be used as a spare resource. These slides provide the observation plan of Sentinel-1. On the left hand, those are the information that you can find actually on the web if you look into this link here. On the left hand side, you see the observation scenario that we are capable to achieve when we have two satellites flying. So it's very simple. We are basically with our observation scenario and with the duty cycle of 20 or 25 or 30 minutes now, we are capable of mapping globally the entire land masses. This is not the case anymore since December 2021, where we have lost Sentinel-1B, which has compromised one of our major requirements, which is our capacity to achieve global coverage. The backbone of the current scenario that we have in place now is that we try to keep or to preserve as much as possible the time series entirely over the world. There is some areas where we cannot, like in North America, some pieces of South America, Africa and Asia. But if you focus over Europe, you can see that Europe still remains our main priority. we are not only acquiring over the land masses, thanks to this specific mode that is the wave mode, we also acquire systematically over the open oceans. Everywhere we don't have any of the other modes like StreamMap, IW and extra wide. Over the oceans, we do acquire in wave mode. The wave mode data is used today operationally by Copernicus services and Meteo services in order to be assimilated in ocean models. So one of the main characteristics of the SAR instrument, and in particular Sentinel-1, is its capacity to provide or to support a very large amount of applications. So you can see here in this slide, I tried to summarize in a nutshell what are those applications. You have applications that are related to marine surveillance, where we can systematically acquire over northern areas and southern areas in order to perform sea ice monitoring, sea ice charting, and also iceberg detection, as you can see here. I think that you see my mouse moving, right? Yes. Another big application for a satellite like Sentinel-1, its capacity to support crises or emergencies, because the SAR, as you all know, is capable to acquire night and day and in all weather conditions. So very often Sentinel-1, thanks to this capacity and also to the fact that we acquire systematically, is one of the first satellites to be or to overpass an area that is that has been impacted by a major event, an earthquake, a flood, or whatever. So emergency support to emergency is one of the main applications of Sentinel-1, especially for floods. In terms of land imaging, here there's many applications like land cover, land use, ground displacement. You can see an example here of deformation that is measured by Sentinel-1 over a mining area, an open mining in Germany. Tectonic volcanoes, forestry. You can see that here it's a global map of biomass derived with Sentinel-1 and pulsar imagery, so C-band and L-band imagery. So supporting forestry, supporting hydrology. You can see here in this image daily mosaics of Sentinel-1 providing. I think it's not daily. I think it's a weekly mosaic of Sentinel-1 providing soil water index, so for supporting hydrology. And another very important application of Sentinel-1 is also supporting climate and the monitoring of climate changes. So we perform systematic monitoring over the glacier, measuring parameters like the ice velocity, the swell, thanks to the wave mode, but also we can image over tropical storms. So one of the main it's not a mission. One of the key characteristics of this instrument is that it doesn't have one single application. It can cover a very large panel of applications. Copernicus and Sentinel-1 is an operational mission, but it's also a game changer for science. As you can see here, the number of publications based on scientific publications based on Sentinel-1 have increased almost linearly since the launch of Sentinel-1. And if you can look at this paper that I've done a very nice bibliometric analysis. So you can see in this cloud the classical topics that are used for Sentinel-1. You can see INSAR, soil moisture, so the one that we have been mentioning, hydrology, ground deformation. But also you start to see, thanks to the fact that we have acquired a very large amount of data over the time, since more than 10 years now, you can see a lot of new topics like machine learning, Sentinel-2, fusion. So more and more user scientists are not using Sentinel-1 data alone, but are capable, thanks to the huge time series that we have, are capable of making science, merging Sentinel-1 with other missions like Sentinel-2, putting in place very impressive techniques for retrieval of geophysical variables. And I think this is my last slide. I know those are backup slides. I think this is my last slide, yes.
Thank you very much, Nuno. Thank you for the presentation. I have a question to ask you. If you can you consider Sentinel-1 able to
detect sand dune movements?
Oh yes, yes. Clearly, we do acquire over the deserts. You can see he can see there. We do acquire over the deserts. Either it is Sahara, not anymore Sahara, but you have the Arabic Peninsula, where it has been demonstrated that it is possible to follow the sand dunes, specifically at seabed. Because we are not penetrating that much in the dunes, so what we see are the dunes. Contrary to what happens at other frequencies like L-band, where the signal is penetrating much more, and what you actually see is not the dune themselves, but you see the hydrologic network under the dunes. But with Sentinel-1, yes, it is really possible to monitor the movement of the dunes.
Thank you.
So we'll go on to the next presentation of Sentinel-2 by the Sentinel-2 mission manager, Ferrand Gascon. So please, Ferrand.
Okay, so I will proceed continuing with Sentinel-2, the second family of the Copernicus program. Yeah, so we'll provide in a few minutes a quick overview on the Sentinel-2 mission. So Sentinel-2 is an optical multispectral mission for the monitoring of land and coastal regions. Like Sentinel-1, it's also a constellation of two satellites, the A and the B unit, which are located in a sun-synchronous orbit at 786 kilometers in opposite locations within the orbital plane. So Sentinel-2 has a local time descending node, which is the time at which it crosses the equator of 1030, so it's a morning imaging sensor, and it has a swath of 294 kilometers. On the plot here in the middle, you can see how the Sentinel-2 bands located here in gray compare to a sister mission, which is Landsat. So you can see the coverage of Sentinel-2 at 60, 20, and 10 meter spatial resolution, covering the visible domain, the near-infrared domain, and the shortwave infrared domain. So like all Copernicus program, the data are free and open, and these data of Sentinel-2 also fit a large range of applications that I will briefly provide a brief overview later. So in terms of schedule, the launch of the first two units took place in 2015 and 2017. So the third unit, the Sentinel-2C, which will replace Sentinel-2A, will be launched in spring next year. And then the A unit will be placed in a parking position, waiting eventually to come back into operations if the C or the B units would fail. So the baseline is to keep two satellites in operations and to provide continuity with two satellites in operation and a third one in spare. Regarding the C unit, the fourth one will be launched in a window between 2025 and 2028, most likely arriving in 2028, and will ensure the continuity of the constellation up to the arrival of the Sentinel-2 next generation mission, which will be launched for the first unit in 2033. Regarding the Sentinel-2 next generation, so the idea is to provide, first of all, continuity of the current measurements, but beyond that, to provide expanded measurements compared to Sentinel-2 first generation. So improving by a factor 2 the spatial, spectral, and temporal coverage of the first generation. Regarding the mission products, so on the upper side of this table, you have the core products. You have, first of all, a product in radiance in sensor geometry, and then two products in cartographic geometry, the level 1C and the level 2A. The first one, level 1C, in top of atmosphere reflectances, and level 2A in bottom of atmosphere reflectances. Then we also have two pilot products, the Harmonize and Fuse product, which combine the data from Sentinel-2 and Landsat 8 and 9 missions, so providing a more dense time series for users. So the difference between the Harmonize and the Fuse is the Harmonize keeps the native resolution of the Landsat and Sentinel-2 of the respective missions, so 30 meters for Landsat, while the Fuse product brings the Landsat resolution to the special resolution of Sentinel-2. Regarding the observation scenario, this is the coverage of the mission. So since last year, the mission has a full coverage of all land surfaces, so including all small islands and atolls. And here on the graph, you see the revisit between the different areas. So most of the land surfaces are covered with a 5-day revisit, while some sea areas are covered with a 10-day revisit, as well as Antarctica. Beyond the nominal observation scenario, we also perform ad hoc acquisition campaigns like this one, which was performed during last Antarctic austral summer, where we covered all the Antarctic surface within reach by the mission. So in case you would have needs beyond the nominal observation scenario, ESA is open to take into account or to consider your request in terms of additional observations. Now moving to applications, in this graph, in this slide, I summarized the usage of Sentinel-2 within the different Copernicus services. And here in yellow, I've highlighted the applications related to the focus of this training, which I understood is on hydrology. So for instance, for the land monitoring service, here in the middle, there are products related to snow coverage, land cover products, which provide information on water bodies, etc., which are relevant for hydrologic applications. As another example, for instance, for the climate change service, there is also information on glacier mapping and glacier flow, which can be related to hydrology applications. So here an example of a product which has been added to the Copernicus land service recently. It's a land cover map, a worldwide land cover map, a 10-meter resolution, which provides within one of the classes, for instance, the permanent water bodies that you can find in this map. So this is a kind of more static information, providing information on the water bodies on a yearly basis. Then there are other products, more near real-time products, which map the water bodies in near real time, allowing to have a following in time of the extent of the water bodies. Here another example related to hydrology. In this case, Sentinel-2 is being used for measuring, for monitoring the meltwater surfaces over Greenland, so due to the impact of global warming. And I think that's the last slide. So just another example where Sentinel-2 time series are used for the long-term monitoring of an area in combination with Landsat in order to, in this case, an agricultural application for the monitoring of these pivot irrigated fields. And with this, I conclude my presentation. Thank you very much for the attention and enjoy the training.
Yeah, thank you. I have a question about this pilot products harmonized between Landsat and Sentinel. So is it related to this NASA initiative? Is HLS products, or it's something that ESA developed? Something new? And also where this data will be available, and only on demand, like orderable or immediately accessible? Because, you know, I mean, how we can use this data? We'll be able to use this data. Thank you.
Good question. So indeed, these products are the equivalent on European side to the NASA HLS project. So the difference between the two products is the fact that in the NASA project, they bring Sentinel to Landsat. So they kind of degrade the spatial resolution of Sentinel-2 to bring it to Landsat spatial resolution. So they provide products at 30-meter spatial resolution, while in this case, the European Copernicus product provides the products either in native resolution, in the case of the harmonized product, either the full-time series at Sentinel-2 spatial resolution. So there is a fusion process where Landsat products are improved in resolution. There is a kind of fusion. There is a fusion with Sentinel-2 data, taking the closest Sentinel-2 product, and then improving the Landsat spatial resolution. Then these products will be, as indicated in the slide, are still pilot products, so they are not fully fledged operational products for Copernicus. And pilot products mean that we offer them on a trial basis for the time being, and they will be made available as indicated in the slide as from last quarter this year through an on-demand service on the OpenEO platform. So further details will follow. There will be news, dedicated news on that, providing you more details on how to access these products on demand. So there will be quotas associated to each user, and the processing will be done on demand for each user.
And we will move to the next presentation, which will be done by the Sentinel-3 Data Quality Manager, Pierre Femenias. So please, Pierre.
Okay, so good morning, everyone. I will give that presentation on behalf of the Jérôme Bouffard, the ESA Sentinel-3 Mission Manager. So I'm Pierre Femenias, the Altimetry Data Quality Manager. So following the presentation by my colleagues on Sentinel-1 and Sentinel-2, Sentinel-3 is a multi-instrument and multi-thematic Copernicus mission, which aim at providing a continuity with the past ESA mission, ERS-1, ERS-2, ENVISAT, and CRYOSAT. ERS-1, which has been launched already more than 30 years ago in July 1991. The main objective that we also call the primary objective of Sentinel-3 is to measure the ocean surface topography, ocean and land surface temperature, ocean and land color, so with a high accuracy and reliability. Other objectives, which are also of importance, are to support application on vegetation and atmospheric, and to cover inland waters, sea ice, and land ice products. So on this slide, you can see some animation of Sentinel-3 products. As for Sentinel-1 and Sentinel-2, it's a constellation of 2 satellites flying on an orbit plane separated by 140 degrees, mainly for ensuring the data coverage of the altimetry mission. So we have Sentinel-3, which has been launched in 2016, already 7 years ago, and followed by A3B in 2018. And the 2 satellite platform and payload are working nominally. We still have long years of operations. Anyway, C and D, the following Sentinel-3 mission, are already ready to be launched. They are today under a storage tent, waiting for the launch to happen. Not before 25 for 3C, and later, not before 27 for Sentinel-3D. In terms of payload, you can see that there are 2 clear payload on board Sentinel-3. We have an optical payload with the OLSHI, which is a successor of MERIS, which was on board ENVISAT, and the LSTM, which is the successor of the ATSR, which was also on ENVISAT. On the topography side, we have a radar altimeter with a 2 mode, SAR mode and a LRM mode, knowing that Sentinel-3 is operating the altimeter in SAR mode full time, 100% of the time. And we also have a microwave radiometer and a POD system composed of GPS, a GNSS, DORIS instrument, and a laser retroreflector for the orbit determination. In terms of responsibility, so differently from Sentinel-1 and Sentinel-2, this mission is operated in collaboration with EUMETSAT. EUMETSAT is responsible for the operation, maintenance, and evolution of the marine parts, so all the ocean, coastal areas, polar ocean. So they are responsible for this, and also for the NRT atmospheric products. On either side, we are responsible for the offline NTC, non-time critical atmospheric, let's say, payload and product, associated product, and are responsible for the land part. Land there meaning inland waters, and the cryosphere, sea ice, and land ice. So application coming from the optical products, as you have seen this summer. This summer was quite dramatic in terms of severe heat waves. So that's kind of map where we can derive from the SLSTR with the surface temperature and which highlighted very high temperature like 45 degrees in Bucharest or in Rome. We have other applications like the ability of identifying wildfire, and we have maps, trends, wildfire atlas, which can be derived from the SLSTR sensor. With the topo payload, we have the ability of monitoring the water surface height over rivers and lakes. And on this slide, you can see, let's say, plots which have been generated by the Copernicus Global Land Service, with monitoring more than 23,000 rivers and lakes all over the world, out of which 19,000 are coming from the S3A and B constellation. And there, I don't know if you can see my mouse, but we have been monitoring the Copernicus Global Land Service have been monitoring the height of the water reservoir for many time, up to the point where the dam of this water reservoir was destroyed in June this year, and you can clearly see the drop in the water monitoring. So that's just an example, but we can do a lot of generating time series over many rivers and lakes with a very high precision, and the precision is coming from the ground processing that we are improving on a regular basis. So on this slide, you can see first on the world map all what we call the virtual station that we can monitor all over the world. So it covers the rivers, lake mainly. And we started with a precision at the time of the JSON 3, which was about 41 centimeters. With the old Sentinel-1 and B altimetry products, we went down to 27. And since let's say a few months, we issued a new, what we call processing baseline, new ground processing, improving the content of the ground processing of the level 2 product, and we went down to a precision of less than 6 centimeters over this river, which is in France, which has a width of 150 meters. So that's quite impressive result in terms of ability that we can do in terms of monitoring rivers and lake. Talking about application with the Sentinel-3, so as I said, EUMETSAT is responsible for the ocean topography that support the global and regional mean sea level trend and answer to the climate expectation, support meteo, but also understand of the oceanographic signal, the mesoscale, Celtic change, and their associated impact. Over land, with the sea ice, we can measure the freeboard, which is the height of the sea over the water, which allow to derive the sea ice thickness, so the thickness of the ice. This clearly allows to better understand the related to the thermoline circulation. Over land ice, we measure the ice sheet, the height of the ice sheet, but also caps, the ice caps and glaciers, which is related to the clearly a contribution to the global and regional sea level. And over water, as already mentioned, we can measure the water surface height, which is directly related to a river discharge and has an impact on the coastal ecosystem. And clearly, all these aspects are interconnected. Okay, to say a few words on the thematic product that we recently improved. That's for the hydrology product, and you can see that with the new thematic products which have been issued recently. You can look for the recent web news from ESA. And we also reprocessed recently the full mission of S3 and S3B. So the full mission data set is available today in so-called thematic level 2 products. So we clearly improved this product with a reduction of the noise over hydrology. Over land ice, we also improved the data coverage, recovering a lot of data on the ice margins of the ice cap, Greenland and Antarctica, and with the improved quality and recovering the data over the ice margin is very critical for understanding the evolution of the global warming. And the last point is on the sea ice, where we did improve the quality of the Sentinel-3 data, and we are today very close, almost equivalent to the quality of the performance of the cryosat data, which is a mission dedicated to the cryosphere. And that's the same for Antarctica, where we have very similar product and similar performance for the two missions. If you want more information, you can go on the Sentinel-1, where there are news dedicated to these thematic products. That's another way of talking about the inland water. So that's a kind of poster summarizing the performance of the products. I will share the presentation with you. You will see that there are QR codes if you want to access the data, the full mission reposting data set and so on. That will be possible to you. Obviously, it's all the data are free and open to anyone. So we have all these scientific products, but it's also very important to ensure the validation of these products. So we triggered about 2 years ago a major activity called the street art, looking into the provision of what we call fiducial reference measurement, kind of improved, I would say, in situ measurement to validate our product. And this activity was very successful. We've done a lot of deployment campaigns, and we demonstrated the good value of our product. This activity will be continued with a street art follow-on by the end of the year. So if you are interested in FRM, you may look at this ITT that will be issued nominally early next year. And the idea is to ensure the provision of FRM to the Sentinel-3 altimetry mission for about 4 years, which will be the duration of this activity. Okay, beyond quickly beyond the Sentinel-3, clearly there will be other mission that will continue beyond the Sentinel-3, like the LSTM for the land surface temperature monitoring, but also Crystal, which will focus on the cryosphere, and later on Sentinel-3 and new generation topography and Sentinel-3 new generation optical. And I think that's all for me with this.
Thank you very much, Pierre.
Thank you for the very nice presentation. I have a question regarding the future altimetry missions. I know about the planned Sentinel-3C, Sentinel-3D satellites, but as far as I'm concerned, as I know, it will be similar to the currently operating Sentinel-3A and B. And what about the new wide swath altimetry, which has been presented in the recently launched SWOT satellite? Is ESA planning on developing similar technology or using the wide swath in future altimetry missions? Thank you.
Okay, thank you for your question. Very good question. Clearly, Sentinel-3 C and D, as I showed in my presentation, they are already built, and clearly they are clones of S3A and S3B. So the features, the instrumentation is identical, and the operation of 3C and D will just be a continuity of the 3A and B. For the SWOT, yes, what I just showed in my last slide, the one before that one. The Sentinel-3 new generation topo will nominally be white swath altimeter. That's I guess today the understanding. We have been waiting for the launch of SWOT to confirm that hypothesis. But considering the result of the SWOT mission, the success of the SWOT mission so far, clearly the Sentinel-3 NG topo with that technology. Did I answer a question?
Yes. Okay, perfect. I see we have one other question.
Hello, and thank you for your presentation. I work on flash flood modeling on ungauged catchments, and you talked earlier about how we can get water height from the Sentinel-3 data. It's a good precision. My question is, what is the minimum river width that we can apply this method on?
First, you need to make sure that we are acquiring the river and the lake with the radar altimeter. We have on board the Sentinel-3 altimeter mission. We have what we call the OLTC, on board the tracking open loop tracking command. So we are giving to the instrument an a priori knowledge of the height that we want to measure. So we have this OLTC table, which is uploaded on board Sentinel-3 and S3D, that we update on a regular basis. So we have, I think, more than 70,000 targets which have been defined of rivers and lake. So we need first to make sure that your target, the river or the lake that you are looking at, is part of this table. First, we need to make sure that S3 or S3B is overflying the target. Then you need to make sure that there is an a priori information within that table. And you can interact with us. If you go on internet looking for the OLTC or the website, Hydro website, you will be able to see if the lake or the river you are interested in is part of this table. Then to come back on the width of the river, we've done acquisition over even the canal DVD in France, which is a few meters large. So we can retrieve a signal from very narrow area water surfaces. But you need to make sure that we overfly, that we instruct the instrument to measure over this specific target.
That's perfect. Thank you very much.
Thank you very much, Pierre. And we will move to the next presentation. Next presentation will be done by Malcolm Davidson, mission scientist for the ROSE-L mission. Please, Malcolm.
Okay, it's my pleasure to present to you briefly one of the future synthetic aperture radar missions called the ROSE-L, which is also a Copernicus mission. And ROSE-L in this case stands for the Radar Observation System for Europe at L-band. And like many of our projects, there are a lot of people behind the scenes making this mission possible. And I've included a list of the main ESA people involved. And we also have a mission advisory group and many contacts with the user community to help design the system and make sure that it is fit for purpose. I give you an overview, and it builds on the previous presentation on Sentinel-1 first generation. We often call them FG now for first generation. And this diagram shows why. What you have here is sort of a roadmap for radar missions. Oops, sorry about that. In Europe, starting with the Sentinel-1 A and B that were just presented, and the soon-to-be launched Sentinel-1 C and D, which are in essence copies of Sentinel-1 A. So they are all part of the same. They all have the same design and the same capabilities to a great extent. And if we look to the future, we see that around 2028, we have the ROSE-L mission, which is an L-band SAR mission. And one of the big characteristics of ROSE-L is the use of this new frequency for Copernicus. L-band SAR is a longer wavelength and contains information which is both unique which is not yet provided by C-band SARs such as Sentinel-1, and complementary to those of Sentinel-1. And then looking into the future, I won't talk about it here, but investing in the use of Sentinels, you can see that there's a long-term guaranteed supply of data, and Sentinel-1 next generation is currently about to be started in terms of the implementation, starting probably sometime mid next year. It's already been studied quite a bit and will guarantee the continuity of your work, your investments in the use of C-band SAR. Starting around 2032 now is the expected launch date. So there are key elements of the Copernicus program that are supported by Roselle and Sentinel-1 next generation, which are providing new information not yet available, so addressing information gaps, and providing enhanced information, which is enhanced continuity. So as you can see, the future is bright in terms of European SAR missions. Roselle, just like Sentinel-1, is a multi-objective mission, which is sometimes challenging to address, but for which we already have the experience with Sentinel-1 first generation. And some of the main, just like the other Copernicus missions, the mission addresses operational services at the European level, and then downstream applications that build on these services and on the capabilities of the missions. Some of the main applications you have listed here, ranging from geohazards, such as deformation and landslides, where there's some unique information that is provided at L-band. Similarly, for land use, agriculture, and forestry, these are all over land. Soil moisture is one of the big promising applications of L-band SAR, and I'll have an example slide on that. And Roselle is also expected to contribute greatly to areas such as cryosphere in the Arctic. Some of the examples that you saw in the Nuno Sentinel-1 presentation will be greatly enhanced through L-band, marine monitoring and of various kinds, first icebergs and also looking at ocean surfaces and winds. So that in essence illustrates the overall application context and the varied application context that Roselle supports. I'll give you a couple of examples which I hope are close to your own area of expertise or interest. One is geohazards monitoring, so being able to sense from space almost at the level of 4 or 5 millimeters the movement of the surface. And here you have a nice example of what L-band brings on the right-hand side. So what you have here is a landslide area somewhere in Russia with, shall we say, if I concentrate on the right, you have the Sentinel-1 example, which is at C-band. And you can see that there is vegetation around this landslide area. So where there is no vegetation, in this case, the points indicate the amount of displacement over time along the line of sight. And you can see that where there is color, that means information. That is where you get some information on the surface movement across the line of sight. And you can see that for Sentinel-1, this is focused mostly in areas where there is no vegetation, because you get sufficient coherence or sufficient correlation from one acquisition to the next to make that estimate. So you get a lot of information in the actual area without vegetation, but very little outside of this perimeter, outside where there is more vegetation. Whereas for L-band SAR, and this is what we will be getting operationally in the future from Roselle, you can see that there is a fair bit of information even outside of the area where there is vegetation. So one of the fundamental and unique characteristics of Roselle is that it will provide surface motion information in areas which are not yet accessible. And you can imagine that in some cases, this surface motion corresponds to things such as big amounts of rainfall or, shall we say, instability on the slopes due to the subsurface hydrology and all sorts of other connections to the applications that you are interested in. So that is one area where L-band brings something unique to and brings unique information. Another one is soil moisture. L-band is a longer wavelength, 23 centimeters compared to 5 centimeters for Sentinel-1. And so when you observe over land, you actually penetrate much deeper into the vegetation than you would at C-band. And that's useful if your main interest is the soil moisture below the canopy. And here we have an experiment that was carried out in Germany some time ago. I think it was back in 2020 or something like that, where you have a field that has been, where part of a field has been irrigated. And I'll draw your attention to the top part of the field and the colors there, where red indicates, shall we say, some irrigation. And you can see that for L-band, this area here to the right, which is not picked up at C-band, is picked up nicely at L-band as it penetrates and senses a different soil moisture condition below the surface. I must say we are still at the beginning. There is an operational soil moisture product that is provided by Sentinel-1 within Copernicus. We're still at the beginning, but we expect and fully expect that L-band SAR will greatly contribute to soil moisture mapping in an operational way across Europe and across the world. Again, there is global access, and the Roselle has many of the characteristics of Sentinel-1. I have one more slide here, which is the Roselle mission in brief. And those of you familiar with Sentinel-1 will see some similarities. There's a constellation of 2 satellites in this case. It's being implemented in terms of continuity of service with Sentinel-1 first generation, next generation. One of the things that I would like to point out is that we have, for Roselle, improved coverage. The Roselle mission has more minutes per orbit than Sentinel-1 first generation. We're around 37 minutes per orbit, so a bigger duty cycle. It's on more often, much more of the time, and can image more things over land. So that's one of the attractive features. The launch date I've told you about, it has, similar to Sentinel-1, the idea that it will only use 1 or 2 operational modes. So there will be no mode switching for experiments here or there. This is a mapping machine, and it will maintain the same modes for most of the time, so that you get guaranteed time series of consistent measurements to use in your applications. The resolution is higher. It's 50 square meters, which is roughly speaking 5 by 10 meters, compared to the 20 by 5 meters of Sentinel-1. That has good sensitivity and so on. And one of the, I think, outstanding characteristics of the system is that it flies in the same orbit as Sentinel-1, so that you essentially have 2 frequencies, not for the price of 1, but 2 frequencies which are co-located, and you can exploit and make use of the information, the different information from Sentinel-1 and from Roselle in a consistent fashion. So those are important characteristics that are promising for the various applications. And that's the end of my presentation.
Thank you very much, Malcolm. Do you have any questions?
Thank you, sir, for your presentation. I was wondering if we can use L-band or C-band SAR for water quality monitoring, or like water turbidity. Like if we can link the sticky disk test with the penetration of L-band or C-band.
That's an interesting question, a difficult one to answer, to be honest. The water quality typically shows up in terms of color in optical systems, which you cannot, as you can imagine, at radar frequencies, you don't really see color like we do in optical. So if the question is, can you sort of detect the water quality through color? The answer is no. Where I think Roselle and C-band SAR, and Sentinel-1 can contribute is, one is a consistent mapping of water bodies. It might seem like a simple thing, but at the global level, it's actually quite difficult to get a consistent map and updated maps of water bodies. They tend to, there's seasonal elements, there's various qualities of maps and so on. So that is one. The second is for the hydrology at high resolution. The only source of soil moisture information at high resolution tends to be from radar. So if you're looking into hydrology with runoff, how much is the runoff expected to be down a hill or within a catchment, and you want that information at the level of, shall we say, sub-kilometers, then C-band plus L-band is a promising combination to get that information and to improve your hydrological models.
Thank you. So thank you, Malcolm.
Yeah, very welcome. Thank you. Have a good course.
Thank you. So the next presentation will be by Matthias Drusch, the mission scientist for the Earth Explorer Flex mission. So please, Matthias.
Thank you, Espen, for the introduction and also opportunity to present here the land surface temperature monitoring mission. I'm just going to share my screen. Okay, so the idea here is to present what has been prepared and designed over the last, I think already 8 years, more or less, leading up to the land surface temperature monitoring mission, which is part of the 6 expansion Sentinel missions, which you have heard about already quite something about over the last hour or so. This is built really on the expertise of a large group of experts across Europe, and you might recognize some of the names here on the first slide. They are part of the mission advisory group. They are scientists, they are institutional representatives from also the European Commission, but also from the European Space Agency, to make sure that we build the right satellite responding to the right user requirements. And I will just introduce you why that is very much needed. So land surface temperature is obviously related to climate warming, as the parameter basically is taking the temperature of our Earth. And as you see here from the IPCC assessment report from last year, you see that we can respond to 3 of the different of the main climate risk part of our region in Europe, but also globally. And the main part we are focusing with this mission as main mission objectives is about water scarcity and link to agriculture production. So you have key risk and key risk 2 and 3, which are very much addressed. We're trying to get the right information about how much water is being lost by agriculture fields or crop, and with that you can improve the crop production or avoid losses in crop production, as key risk 2 is being mentioned. But I mean, that is not all. We also obviously as humans are being stressed by heat factors, and that can even lead to mortality and increased mobility in the population. So that is related to urban heat islands or heat waves, which we have all experienced over the last summers. So that is leading us to the main mission objectives. That is provide high spatial and temporal resolution of thermal infrared observations, which in the moment don't exist in that appropriate resolution. In support of agriculture management services. You see here on the side, more crop for the drop, basically. So more biomass coming out of agriculture production while using less water, but reducing the evapotranspiration. And additional applications, just like I mentioned, the urban heat islands, for example, management and planning related to that. In terms of technical features, you have here the different mission requirements. They are based on the user requirements driven by the main mission objectives, so the agriculture productivity. And here we look at improving the measurement of the evapotranspiration with high accuracy and precision at field scale. So field scale in European Context is defined here as 0.5 hectares. And because evapotranspiration/irrigation practices are changing every day, so we need daily observations. And for that, I will come back to most of these technical points over my next slides. So I will jump forward, but the main observational requirements are here translated from the user requirements into 50-meter resolution, daily revisit, and with the accuracy of 1 to 1.5 Kelvin of the land surface temperature. That is what we're gonna want to have in the end, addressing on the left-hand side in the evapotranspiration field scale. We have here a prototype basically based on Sentinel-3 and Sentinel-2 fused data sets, where you then really come down to the field scale and getting the actual evapotranspiration. On the right-hand side, you see eco-stress data being sharpened over Milano, and it was last year, and also Paris, but we have done the same thing again also over Rome this year, and I think we had also Toulouse and Madrid. These are experimental data sets still, because it's not, eco-stress is not really an operational mission flying on the International Space Station, but gives us a really very nice, interesting data sets to work with and developing algorithms and understanding how we can use them in the operational management context. So, few words about the data products which we are planning to have. There will be only level 1C and level 2A products, which means basically we will have top of radiances and brightness temperature information and the level 1 level, but then for level 2 we look at emissivity and land surface temperature, which will be operational products, feeding into many different algorithms, and we're really looking forward here to work with the science community, such as you, to develop then higher level products like evapotranspiration and others. We want to deliver that in a high latency, because we want to observe the data and then give recommendations to the farmers within basically 12 hours. So we really have to have a very high latency in terms of delivering the data to the user, meaning also processing them in the meantime. So that's how the mission will be looking like. 2 satellites flying in constellation, which will bring us to a revisit time of 2 days. So we don't get the daily revisit at equator, but over Europe that will be very closely matched. The mean solar local time is at 12:30. Descending, that means that we actually observe the vegetation at the point of highest stress. Then we really can make the best understanding how evapotranspiration and the crop is responding to the heat or the availability of water resources. For that, we need a very large swath. You see here the useful swath is 670 kilometers, and that also will have an impact on the observation angle, and we will look at the directionality of the observations in doing our preparation in the moment. It's a land mission, LSTM, land surface temperature monitoring. So we look here at the coverage of acquisition, global scale, which is very similar like to Sentinel-2, but there's also some marine areas and coastal areas involved, because the LST would be also very interesting for example coral reefs, but also other applications. And we also assess the Antarctica, because melting of the Antarctica is very much interesting at high resolution as well. The instrument, very shortly, you have here Wisnier and sphere bands, which are very much matching the Sentinel-2 bands, but then we add on top of it, that's really the innovation, it's the 5 thermal bands, so you can retrieve emissivity out of these bands directly. You don't need additional information, and you get also then the land surface temperature retrieved out of it with a high noise equivalent delta temperature, and that's one of the biggest mission drivers for the detector and the optics. Finally, we look into airborne campaigns, and we just successfully closed one this summer with 2 airplanes actually to get really the understanding of the full view angle range, so understanding directionality of the observations in preparation for the mission. And I would encourage all of you for your science projects to use these data sets. They will be made available. The 2021 we can already disseminate. 2023 will still need some processing, but they should be used within science activities. And that is my last slide here. We do work very closely together with our international partners like CNES and ISRO. They are planning to have the Trishna mission, which is very similar in resolution and thermal observation. At the same time, SBG from the NASA, together with ASI, the Italian Space Agency, they are preparing also a thermal mission. Both of them are in the 50 to 70 meter resolution. And then LSTM will be all coordinated, and you see with them, you see on the right side how the coverage will look like, and then we really are looking at daily observations at high resolution for thermal monitoring. With that, I close and happy to hear your questions.
Thank you very much, Ben. Do we have any questions? Okay, no questions, so thank you very much, Ben.
Thanks to you, Espen, and enjoy your class or course.
Thank you. So, unfortunately, the mission scientist for the FLEX mission is not able to participate today. You are very delayed, so I think it's not so bad for the time schedule. I'll just say in 1 minute, I already mentioned it before, this Earth Explorer FLEX, it's our photosynthesis mission. So it doesn't measure the reflectance, it measures the fluorescence coming from the plants. So which is an indicator of the photosynthetic activity. So with this, we are able to measure, in a way, the stress of the plant. And the one of very common stressor of the plant is the lack of water. So that's the main contribution from FLEX to hydrology, is that we can have a kind of very early sign of water stress due to lack of water. It's a mission that is planned for launch in end 2025. It will provide data at a spatial resolution of 300 meters. So it's a bit at the edge for the agriculture application. It's a bit at the limit. But this is, as I said, this is part of the Earth Explorer mission. So it's very experimental one. It's very difficult to detect these very small signals from the fluorescence. So it's a very challenging mission. But there has been some delay on the mission, but as it seems now, it will be launched by the end of 2025, as I said. So will help for the drought part, hopefully, of this hydrology subject.